Thank you very much for this opportunity to present our results here. My name is Simon Mackovjak. I'm from Slovakia, and I work at the Slovak Academy of Sciences. I'm sorry that I wasn't able to come personally to this very nice workshop, but I'm very thankful that I present these results online. And it is the acronym of this project is ASPIS, and it means Autonomous Service for Prediction of Ionospheric Scintillations. And the goal of this project is to perform the feasibility study of if it is feasible to prepare such service. And let me start with just introduction on the frame that we will talk about. And I will talk mainly about the ionosphere and disturbances in this ionosphere. And
I might actually stop you there for a second. Sorry, we're having a tricky time seeing your screen. You're sharing it, but it's not appearing white. There we go. Okay, sorry.
Can you see it now?
Yes, yeah, no, the problem on our end. Don't worry about it. Maybe if you can just go back one slide and we'll catch up.
And this was just introduction. And yeah.
Brilliant, thank you.
Thank you. So I will focus on the scintillations, and this is the effect. So when the radio receiver is communicating with the GNSS, so basically the GNSS receiver, when it's communicating with the GNSS satellite on the orbit, and when the signal propagates through ionosphere, the signal can scintillate through the presence of some disturbances. And basically, the objective of this project is it is feasible to predict these disturbances and to develop the service that can provide these predictions. And ASPIS was also the type of shield in the ancient Greece. So basically, also this is the intention to somehow shield it the vulnerable technologies. And the particular goals of this project that is supported by the ESA through the Program for European Cooperating States is to prepare the data and to provide their physics-based explanation, then to develop data-driven model that is based on machine learning techniques that will have the pre-processed data as the input and the ionospheric scintillations prediction as the output. And then to deploy this developed model to work as a service on the AWS cloud with REST API and demonstrate the proof of concept. And now I would like to talk about these particular goals. So at first about the data. So we use the data from the various networks of the GNSS receivers. And until now, we focus on the two networks. The first one is in Canada. It's called Canadian High Arctic Ionospheric Network, or CHAIN. And the second network of the data is from our colleagues from Germany, from Ionosphere Monitoring and Prediction Center, that is at DLR. And these data are available, and mainly this CHAIN data that I will present today are available through their web interface. And we mainly focus on the phase scintillations, and basically the phase scintillation, specifically the parameter called sigma phi, and this is the sigma of the trended carrier phase. And this parameter is mainly important in the polar region. And as we know, when we measure this data from the GNSS satellites, we need to recalculate the values of this data in the time and position, because the position of the satellites is changing in the time in the field of view of the receivers. So we recalculate these values to the specific positions we call the bins for the specific altitude in the ionosphere. And by this approach, we were able to put together the bins on the map. So now we are talking about this Canadian network, so over to Canada. And for the specific time interval, you can see how many data points we have in each bin. So the color represents the different number of the bins. And when we take a look on one specific bin, in this case this one, so we can also plot the time variation of the sigma phi parameter. This is specifically in the October 2021 for 2 days. And here you can see that there were present very strong scintillation. There was present very strong scintillation event, and the sigma phi scintillate very rapidly and in high numbers. So this event we can see also in this map. So basically, you can see the evolution of the scintillation in the space and time. And during these events, so the connection with the GNSS satellites might disappear. And therefore, there is a high motivation to predict such event and to investigate if it is possible to even predict such events. So the baseline for the prediction was the persistence forecast. So basically, we just assume that in 15 minutes ahead, if there are the same values as in the present. And for this simple forecast, we calculated various metrics that are used in the statistics, like precision, recall, F1, and so on. But now I would like to focus just on TSS. It's true skill score, and it is calculated like the ratio of the true positives and false positives events according to this equation. And in this case, the true positive event is when their scintillation occurred, and also our prediction correctly predicted that it occurred. And as a threshold for this decision, if the event occurred or not, is that if the sigma phi was higher than 0.1 radian. So we can see that in this interval from -1 to 1, the true skill score is 0.11. So it's not so bad, but we can see that the predictability is not so not so excellent for this baseline model. But this is just the baseline, and we will try to investigate how better model we can develop. And for this reason, we use the LSTM approach. This is the specific type of the recurrent neural network, but it resolved the problem of the vanishing gradient of this recurrent network. So it's very convenient for this type of the task. And we utilize the Python framework language and the frameworks, and also the LSTM already involved in the TensorFlow and Keras libraries. Okay, so for this deep learning approach of the time series forecasting, we used various experiments. So at first we do some autoregression model, then multivariate model when we concatenated several LSTMs also from other parameters, and then sequence to sequence when we try to encoder and decoder and with corporation and LSTM. And a very important step in this process was the pre and post processing of the variables. So basically we tried different training windows. So how large is the window of the data that we are using for our prediction, and also the definition that how far we can do this prediction. Also, it was very important to balance the data set, because these events are very rare. So it was very important to make the proper balancing. And also we evaluate when the scintillation occurred, and also we consider the additional input features. And for this reason, we try to use various parameters from from space weather that are available mainly from OmniWeb. And we also try to rank importance of these parameters. But we have found that there is a quite important problem with the missing values because when we balance our data set, so we have just few windows when this event occurred, and if there were some missing values from the space weather parameters, it was quite challenging to put them together. So therefore, we realized that we try to use as low additional parameters as possible to make this service work in the future without any gaps.
You just have 5 minutes left there.
Thank you. So now I would like to present the results of this deep learning prediction. So just concentrate on this last column. Here is this TSS, the true skill score. And you can see that it's much higher than our baseline, also for autoregressive model and also for the model when we use the KP index as additional index. And here you can see the confusion metrics for that. And you can see that the number of false positive events is still quite high. And I will talk about this number in the next slide. But before that, I would like to say that we compared our results also from the results from Mackovjak et al. 2018. And they did similar analysis, but they use SVM support vector machine as a model. And we can see that our approach that we used, the deep learning approach, is slightly more efficient. And now, just short discussion about this false positive rate. So here we have the time series of the measurements, and we can see clearly when the scintillation occurred. And now we can see by the color when our model highlight the points as a false positives. So we can see that the interval of the scintillation event was predicted correctly, but the classification based just on the threshold 0.1 of the radians for sigma p is not very convenient. So therefore, we would like to just rework the selection of the scintillation periods. And the last but not least, I would like to just mention that we would like to deploy this model to the service, to work as a service. So here is the preliminary AWS architecture. So when the data will be automatically downloaded from the chain repository, and there is a batch job that apply the model and store the results in the S3 bucket. And through API, it will be available through dashboard and for other users, so it can be integrated to other services. So we will be able to provide nowcast. So what is the situation for now from the measurements, and also the forecast 1 hour ahead. And this is the summary. Deep learning approach is useful for prediction of scintillations. So we have seen that we obtained some reasonable results. And we would like to finish this proof of concept, and the end of this project and the delivery to ESA will be in the following months. So we would like to conclude all this work, and we also will submit a paper about this research to the Space Weather Journal. And if you are interested in our work, so you can visit our GitHub, and you will also find some of our other research there. Thank you very much for your attention.
That's great, thank you. Have we any questions here in the room? Or I might ask one if, while people online might be thinking of something. So does this only account for scintillations over Canada then, or the particular areas that you use the network? Because I know there's, trying to do radio imaging with LOFAR, which is based in Europe, it would be great to know when you have ionospheric scintillations and when to avoid looking at the sun and that sort of thing. So is that something you can speak to, or?
Yeah, basically we used for this initial phase just the data from the Canada, but as I mentioned, we also have some data from Europe. So we would like to deploy also the service for this other data from IMPC, and also we plan to be in contact with people from ING from Italy that operate several receivers over Europe. So yeah, for sure, this is the plan to deploy the service for all locations where the receivers are.
Brilliant. Still no show of hands online, and I think we don't have anything else in the room. Maybe one more quick one for me to you and anybody else involved in ionosphere and tech and stuff. Can you use VLF observations of the ionosphere to be of any use?
We haven't considered this yet, but yeah, so we are open for this cooperation or this discussion.
I'm just first thing off the top of my head. But anyway, cool. Thanks again, Simon, and we'll move on to our next talk. So thank you, everybody.
Thank you.